Hello, this is the start of LaPlace Transforms Chapter 7, Section 2, Transforming Initial Value Differential Equations and Transforming Integrals. So how do you transform a derivative of a function? Well, it's quite easy. What we have is a derivative, and we want to find its Laplace transform. To do that, we apply the definition of the Laplace transform, which is this. Now, to do this integral, we have to go back to our friends from Calculus 2 and apply integration by parts. So the integration parts integral is this. Okay, so now we have to find is what is u and what is v, and we're going to choose u and v to equal these, or dv to equal these. If we do that, du is equal to this, and dv, or v, is equal to this. So if we plug it back into the definition for integration by parts, we get this answer for the Laplace transform of a derivative. This becomes very handy. Now if we evaluate it at its limits, we get this. So what happens to be nice here is the exponential, when it goes to minus infinity, is 0. So this term goes away. The exponential at 0 is 1. And we get left with this. And what happens here, this integral over here, well, that's the definition of a Laplace transform for the function f of t. And so our answer becomes this, where the capital F of t is the Laplace transform of f. And so that is how you find the Laplace transform of a derivative. So now that we have the Laplace transform derivative, what do we do if we have a second or third order derivative? Well, we apply the same ideas. So we know this is the Laplace transform for a derivative. So I want the Laplace transform of a second derivative. So what I'm going to do is play a trick in which I make the second derivative of f equal to a function called g prime of t. This allows me to plug into this place as this, which is a first derivative, and I have a way of calculating a Laplace transform for a first derivative, which is shown here, where g of s is the Laplace transform's derivative of function g. And then, well, what is g prime of t? Well, that is the first derivative of f. And so if I make my substitutions, what happens is the second Laplace transform of the second derivative of f is equal to s times the Laplace transform of the first derivative of f minus the initial position of the first derivative of f. And so now I just plug in a definition for the Laplace transform of the first derivative of f, which we've already done. And we do that, we get this, we carry out the multiplications for s, and we get this definition. Notice that I have s squared times the Laplace transform of f minus s times the initial position of f minus the first derivative initial position. And then this can be carried out to multiple orders of differentiation. We just do the same procedure twice. And again, you get the third power of s times the derivative, the Laplace transform of f, and minus s squared of the initial position of f minus s times the first derivative, its initial position, minus the value of the second derivative at t equals 0. And this can go on and go on and go on. It allows us to take the Laplace transform of any derivative. You can also take a Laplace transform of an integral, and this is the definition of that. It turns into the Laplace transform of the function you're trying to integrate divided by s. And then, of course, if there's a Laplace transform, there's an inverse Laplace transform. When would you do this? Mostly you would do this when you're taking inverse Laplace transforms, not when you're taking Laplace transforms. It can come in handy in time. All right, how to use this actually? Well, we can use this actually this way. Let's take this differential equation and let's solve it using Laplace transforms. I'm first going to calculate the Laplace transform of the whole equation, and then I have to distribute the Laplace transform across the whole equation, and I get this. and then I will evaluate the Laplace transfers of each individual function. In doing that, I get the Laplace transform of my second derivative. I have the Laplace transform of x times 4, because 4 gets pushed out front, and then I have the Laplace transform of cosine of t. Now, if I put everything in terms of Laplace transforms, which is my capital X and my capital X here, I can evaluate this expression using my initial conditions. And if I do that, the initial condition of the position at t equals 0 is 0, and the initial position of my first derivative at t equals 0 is 0. That leaves me with this expression. Now I can solve for capital X. And I'm doing that because that will tell me the Laplace transform of x. And why do I want the Laplace transform of x? Because I'm trying to solve for x of t. How do I do that? Now that I have the Laplace transform of x, I have to have the inverse Laplace transform. The problem is, if you look in your table of Laplace transforms, you will find no functions displayed in this manner. I have to turn it into functions or sums of functions that can be displayed in this manner. And what I'm going to do is I'm going to claim I'm going to write this fraction in terms of this fraction. Notice if I have an s squared plus 4 here, what I can do here is I have to have an s on top for my partial fractions. So using this definition, I need to find a, b, c, and d. So we do our partial fraction procedure. I find the common denominator. Then I expand the numerator, and I have to have the numerator on the right-hand side equal the numerator on the left-hand side. So I need to simplify the right-hand side. If I do that, I get this. I've grouped together all the coefficients with s cubed, s squared, s, and the ones without any s are constants. Now I have to make the right-hand side equal to the left-hand side. To do this, the coefficient in front of s cubed has to be 0. The coefficient in front of s squared has to be 0. The coefficient in front of s has to be 1. And the coefficient in front of b plus x of d has to be 0. If I do that, I have 4 equations and 4 unknowns. If you solve them, you will find out that a equals minus 1/3, b equals 0, c equals 1/3, and d equals 0. Now I'm going to go plug them in back into my definition that I set up for the partial fractions, and I get this expression. Now I can do an inverse Laplace transform of this expression because these show up in the table of Laplace transforms. Well, what is an inverse Laplace transform? I have to take the inverse Laplace transform of this. I can distribute it, and then that will give me x of t. How do I find the inverse Laplace transform? Well, here's how I find it. I find the Laplace transform by distributing it across, the inverse Laplace transform by distributing it across, and then once doing that, I can factor out constants, and then these functions show up in the tables. If you look up on the tables in the cover of your book, you will find that this Laplace transform is cosine 2t, this Laplace transform is cosine t, and this is my solution in x. And we're done. We have found it. How about we do one more example? So we do one more example. We do this way. Again, this is our differential equation. These are our initial conditions. I want to find the Laplace transform of the whole equation. I distribute the Laplace transforms across the whole equation. Now I take the individual Laplace transfers applying the rules that I know. There's my Laplace transform of the second derivative. There's the Laplace transform of x. Here's the Laplace transform of cosine of 3t. You can find all these in the table in the front cover of your book. I evaluate the initial position. I evaluate the initial velocity. I come up with this expression. I need to solve for capital X of t. If I solve for capital X of t, I get this expression, and then I end up with this expression. Again, I need to write this in terms of partial fractions. So to do this, I need to simplify my expression. And if I simplify my expression, I come up with this. I carry out the multiplication, I get this. And so this is what I'm going to use for my partial fractions. So by definition, I'm going to take this function and set it equal to this function, because I'm using my roots down here at the bottom, and as individual fractions, I'm going to find out what fractions I need to add together to get the left-hand side. Again, we do the same thing we did before. Find a common denominator. Once I find the common denominator, I take the numerators and set them equal from the left-hand side and the right-hand side. Multiply out the numerator for the right-hand side, and I get this expression. Then I'm going to set the coefficients equal again. So coefficient in front of x cubed is 1. The coefficient in front of s squared is 0. The coefficient in front of s is 10. The coefficient in front of the constants is 0. So I again got 4 equations and 4 unknowns, and we can solve this system. And if you solve it, you'll find out that a is a negative 1/8, b is 0, c is 9/8, and d is 0. And then we have to find x of t. So this is my solution for the Laplace transform of x, capital X of s. And so I need to find inverse Laplace transforms. And then I have to distribute the inverse Laplace transform across each individual fraction, and we can do that. Laplace transforms have this property. Again, I can factor out the constants, and I get a Laplace transform of this function, and then another one of this function. These functions here show up in the table. If you look in your table, you should find this is cosine 3t, this is cosine t. And so this is my solution in x. And we're done. It gives you the homogeneous and non-homogeneous solutions at the same time. In the homework, you're going to be asked to solve a system of equations. It's the same way we've done it before. Take the Laplace transform of the systems first, then eliminate the capital X or the capital Y, and then solve for the final Laplace transform using the same procedures we discussed here. Thank you, and see you on Friday.